Please go ahead.
So thank you. Good afternoon, everyone. My name is Kromer. I'm working at the Institute of Research and Technology, Saint-Exupéry in Bordeaux. We are working for aeronautic and aerospace industry, but associated to academic institutes, which is Mechanical and Material Institute from Bordeaux. Today I will present you my work on discrete element method to study the powder bed layer characteristic in additive manufacturing. As it was presented Monday afternoon, additive manufacturing presents a lot of benefits for the designer and for manufacturing. However, the objects being fabricated are now dedicated to prototyping or for static structure, because in this object being fabricated you have defect formation during the process, especially for laser beam melting. There is around 50 parameters that can affect the defect formation in the part, but three main parameters are can be dedicated to the quality of the part. It's the laser power, the scan speed, and the scanner and scan strategy. However, if we look further into laser matter interaction, so with above the laser light interacting with the powder bed layer, we can see that the laser beam energy can be set thanks to three parameters. But the interaction is associated to this powder bed layer. So we wanted to be more have a more understanding of how this powder bed layer to be able to control it if it's possible, and such as to improve our understanding in laser beam melting and to give some information to the designer and manufacturer. So my presentation is divided in 5 parts. Discrete present you the discrete element method, the model and the analysis have used for this study, few results and a discussion. So discrete element method are based on Kundal and Strack work from 1979. They were inspired from molecular dynamics, but at the mechanician scale, they wanted to have discrete elements such as atoms. So they use spherical shape to represent either a real grain of granular materials, such as powder, sand, rocks, or either a representative volume element. There is interaction between these discrete elements that must be commonly forces and torques, and sometimes it can be more complex. So force torques nature can be associated to the contact nature between the discrete elements. There can be repulsion, adhesion, or friction. We can also use cohesive link associated to volume elements using spring laws, Berners beams, and also they can have distant forces such as magnetic field. To do this work, we use a Gran platform, which were developed at the institutes in Bordeaux, which we can implement discrete element method with this tool. So we use smooth contacts, which can modelize elastic interaction between rigid sphere. It leads to an explicit time integration schemes where it's well adapted to fast dynamic mechanical problems, such as the powder bed layering. We have computed step-by-step the interpenetration between the two discrete elements. And associated to this interpenetration, we can use Hertz contact law to compute the repulsion forces. We also use dissipative force, which can be associated to viscous dissipating force between the two discrete elements. So we needed to implement damping coefficient and critical damping values. And we also implemented the regularized Coulomb law for static and dynamic coefficient between the particles, but also associated to the build platform. And Gran used a velocity Verlet algorithm for the explicit time integration shapes. The model, we try to be as much as near the machine. So we have a build platform from 100 to 50 millimeters square. Could be bigger, but it didn't seem to be interesting to do such volume. We integrated randomly a powder layer volume, which were 20% more larger than the build platform volume. And then we have a recoater system that can spread this powder to create this powder bed layer. So here you can see two drawings. We try to make two recoater systems, a blade and a roller, which can be seen on different additive manufacturing machines. We have our powder bed volume, which will be spread on the build platform, layer by layer, so 50 micron by 50 micron. We will deposit this powder bed layer and do some analysis for the blade and the roller. The main variables we started with was the powder bed thickness and the recoater speed. So we try to understand the effects of the powder granulometry. So we use three types of powder: uniform, Gaussian, and bimodal powders with a mean diameter of 50 microns. We spread a stainless steel powder. The build platform had a friction coefficient associated to a grip plastic surface. And finally, for the analysis, we did post-mortem analysis of the complete build platform. We also described the powder bed layer in several parts. It was 200 micron by 200 micron square millimeter micrometer to have a surface density evaluation. We also calculate the coordination number, so it's a number of contacts between each particle. So associated to the packing density, we can have an idea how the particles interact with each other and how it is packed on the powder bed layer. And finally, we also evaluate the specific roughness, which is the mean height, the mean difference of peaks and valleys from the mean height of the powder bed layer. So now I will present you a few results. So for the fixed velocity at 50 millimeters per second, first from those results, we had two kind of results depending on the recoater system. First, for the blade, we observed that a flatter powder bed layer, but the roller seems more significant impact on the packing density and the coordination number. Roller can introduce more force and can let more arrangement in the powder bed layer. And if we look now more closely on the graphs, you can see that after 200 micrometer for the powder bed layer thickness, we have a steady state. So the powder packing density seems higher for the two distribution, so the bimodal powder, compared to the one size and Gaussian distribution. And we have, in the contrary, highest coordination number for the Gaussian distributions, but it is more practically associated to statically point of view of how the particle can interact with each other. when you have a complete Gaussian distribution. And before, you can see that you have a deviation. I didn't add a standard deviation on the graph, but I tell you that there were large standard deviation for the different packing density. We had to do more tests to be sure that those values were statistically accurate. So we observed a low packing density and coordination number. It can be associated to limited particle arrangement. So the link between the volume and the space for the particle to move from each other. And we also observed higher roughness values. It can be associated to the force exerted by the recoater to fulfill the build platform versus the polarized distribution. The big particles had a large interaction with this recoater and create a hole during the powder bed layering. Now if we look on another point of view, for the two speed, you can see that there is deviation for the first layer on the packing density for the blades, here and here. In the contrary, you will see that it's stable for the roller. I didn't show you the graph, but it was the contrary for the roughness. It's the first interpretation we could do. Also, for this different system, you can see that we had a larger packing density for low velocity displacement, which are associated to arrangement mechanisms between the particles. Roller can compact more efficiently this powder bed layer, and also we can increase the powder bed layer during the process. As you can see, we have always a small shape for the different system and for the different speed. And now if we, from this previous result, we try to be more associated to the powder bed layering during additive manufacturing. So if we keep a previous melted part, which were represented here in orange, so we have the powder bed layer growing each step by step, and we keep always a 50 micrometer here from the top surface of the previous platform. And we observed that when the recoater impacts this melted part, so we have a compaction of the particle around it, which can be associated to an evolution of the packing density, as you can observe here. So this is the first layer. In gray here is the third layer and the sixth layer. Each time in the middle, you can observe that on the melting previous part, you can see that the packing density decrease nearly equally to the first layer. So we have an impact of the velocity of this system, and also with the recoater. So thanks to this discrete element method, we can also use during during this displacement the mean forces of the particles. And as you can observe for the first layer, in gray here you have the Z forces, the X forces, so in the direction of the recoater displacement, and in black it's the packing density. You can see that for the third layer and the sixth layer, the forces associated to the melted part are equal for the first layer. So there is similarities with the first layer deposition when it goes up to the previous melted part. And you have also edge transition that have to be more accurate in this computation. From this work, we try to check experimentally. So here you have some results for different powder bed thickness for apparent density and apparent surface. You can observe that we have for the thinnest thickness a drop of the packing density, and also a drop for the apparent surface, which can say that our simulation gives us a qualitative good point of view, and then we have to try to make it more representative of specific materials. So we will try to make a meta model to create some laws of spreading powder bed layer. And finally, we also did 3D laser profile analysis. So after the recoater deposition, you can see that from a previous melted layer, you have a light intensity variation, which can enable us to see that there is edge effect, a strong magnifying effect here on the beginning and at the end. So we can imagine then if the laser had to go through the same pattern, we will have different deviation of the volumic energy density. So this has to be taken into account for manufacturer and also for the designer. So that's a discussion I wanted to do for design for X, and more specifically for design for additive manufacturing. We would like to help the designer to have more information for qualitative design guidelines to design a 3D CAD model. There is already many work on this specific area, but it will be interesting to have also knowledge on the powder bed layering for the designer, and also for the manufacturer. We have already optimization of grid direction, laser parameters, and scan profile to optimize the additive manufacturing, but there is still a miss for the recoater parameter that can be also optimized for selective laser melting. So to conclude, powder size distribution affects the packing density due to particle arrangement mechanisms. We want now to be more qualitative to help our manufacturer. Recoater type and speed need to be optimized to have homogeneous spatial distribution, and the layer thickness and this layer properties vary with the previous layer. So we have to take into account the shape of the we wanted to manufacture. So for our future work now is to create a recoater shape optimization depending on the part shape. We are now focused on a recoater that can move layer by layer in each shape to be sure that we have an homogeneous packing density. And we also work on an in situ analysis of the powder bed for local volume energy density optimization. So we try to make a pre, during, and post analysis to have a more understanding of the laser beam melting, and also to provide different meta models and statistic tool for the designer and the manufacturer. So I work on the Holopart platform. If you are interested in this work, we can discuss later. Thank you for your attention.
Thank you.